Welcome to AI World TV, your go-to destination for everything artificial intelligence. Discover the captivating landscape of AI, where advanced technology finds real-life application. Subscribe to AI World TV for webzine articles, reports, podcasts, videos, live events, and latest trends. Hear from top industry leaders and discover how AI is transforming industries and our daily lives.
Welcome back to the Deep Dive. Today we are taking a leap forward, looking at the year 2026. This is the timeline when the boundaries of computation are, well, expected to be fundamentally redefined by one explosive force: the convergence of quantum computing and artificial intelligence.
It's an intersection that promises exponential change, and it's no longer just confined to academic theory. Our mission here is to really map out the practical reality of this convergence, what the industry is calling quantum machine learning, or QML.
And to extract the biggest opportunities, but also the most urgent risks that you really need to be aware of.
Exactly.
So by 2026, the foundational technologies themselves, they've matured quite a bit. On the AI side, we're looking at systems that are deeply integrated into our lives, driving incredibly nuanced decisions.
Oh, absolutely. Wow. They're leveraging these massive data sets for machine learning, for deep learning, and achieving near-human comprehension, especially with things like natural language processing. It's the age of hyper-integrated, massive-scale AI.
And at the same time, quantum computing has moved past being purely experimental.
Right. We're finally seeing qubits that are far more stable. The error rates are lower than they've ever been, and you can actually access robust cloud-based quantum services as a researcher.
Yeah.
The power here, it stems from the core principles we all know: superposition, entanglement, those qubits existing in multiple states at once.
So for you listening in, someone who isn't planning on building a quantum computer next week, what are the concrete game-changing benefits of using that quantum power to accelerate AI?
Well, the benefits really fall into three core areas. First, it's about exponential processing power for very specific tasks. Optimization and simulation problems.
Okay.
These are problems where the complexity just grows so fast that a classical computer would literally take longer than the age of the universe to solve. Quantum just cuts through that.
So are we talking about finding the single perfect delivery route for a global logistics network, or instantly optimizing a massive financial portfolio with thousands of variables?
Precisely. The second thing is that quantum systems are uniquely suited for high-dimensional modeling. When you're training a massive AI model, you're often dealing with, feature spaces with hundreds of thousands of dimensions.
Which is just impossible for a classical machine to really handle efficiently.
It struggles, yeah. Quantum computation can model those high-dimensional spaces naturally, which can boost the accuracy and the efficiency of the whole AI training process.
And that third area, the one I find most fascinating, is the simulation power, for things like chemistry and material science.
That is where the power is truly transformative. Classical computers can't even simulate moderately sized molecules because the complexity just scales too quickly. Quantum computers, because they're governed by the same rules as the molecules themselves, can run those simulations accurately.
So researchers could virtually test millions of potential drug molecules or new battery materials without ever setting foot in a lab.
Exactly. It could just revolutionize fields like pharma and sustainable energy.
Okay, let's unpack this convergence. We call the field quantum machine learning, or QML. How does QML actually work right now in this near-term 2026 timeframe?
So QML is the critical field, but it's really defined by the hardware we have today. We're firmly in what's called the NISQ era, the noisy intermediate scale quantum era. The qubits are powerful, but they're also very prone to errors.
So research isn't focused on these massive, purely quantum algorithms yet. It's more a hybrid approach.
It's heavily concentrated on hybrid quantum classical models. That's the practical reality. The classical computer handles the heavy lifting, like data pre-processing, and then the quantum computer performs a very short, specific part of the calculation where you get that quantum speed up.
So it's not purely quantum running the show. The classical computer is like the manager sending these short, noisy bursts of work to the quantum hardware.
That's a great way to put it. And that leads us directly to the most practical algorithms we have today: variational quantum algorithms, or VQAs.
Right, VQAs. This is where it gets really interesting in terms of actual implementation. How does that hybrid feedback loop work?
VQAs are essentially a constantly evolving feedback loop. The classical side acts as the optimizer, the coach. It adjusts the parameters, the knobs in the quantum circuit based on the last result.
Okay.
The quantum computer, the athlete, executes a short quantum circuit, measures the result, and feeds that measurement right back to the classical side to learn from.
So because the quantum part runs for such a short time, the noise doesn't completely wreck the calculation before the classical computer can learn from it and try again.
Exactly. It minimizes the time the computation is exposed to all that noise. The prime example here, the one being aggressively developed for AI, is the quantum approximate optimization algorithm, or QAOA.
And what's a concrete application of QAOA for AI training?
Think about training a deep neural network. That whole process is just a massive optimization problem. You're trying to minimize these incredibly complex, high-dimensional loss functions. QAOA is being tailored to speed up that specific process.
So to find the best settings for the AI model faster, and maybe even find better solutions than classical methods could.
Potentially, yes. Now, beyond optimization, we're also seeing quantum being used to fundamentally change how data is processed through concepts like quantum kernels.
This sounds like a different approach. What's going on there?
It is. Algorithms like the Quantum Support Vector Machine, or QSVM, don't just speed up the classical algorithm, they use the quantum hardware to fundamentally change the data itself.
How? What's the quantum magic involved?
They use what's called quantum feature mapping. They take classical data, say a list of financial transactions, and use techniques like amplitude or angle encoding to transform that data into a massive high-dimensional quantum state.
So you're basically projecting the data into a new space that's, well, it's geometrically inaccessible to classical models.
You've got it. The payoff is that you gain a new, higher-dimensional perspective on the data. Patterns that were tangled up and hidden in 3 dimensions might suddenly become clearly separated in 1,000 dimensions. It helps find subtle patterns classical systems just can't see.
It's a completely different way of looking at the problem.
A different way, exactly. And of course, researchers are also exploring full quantum neural networks, or QNNs, but there are some major hurdles there.
Right, I've heard about this, the famous barren plateau issue. That sounds like a big roadblock.
It is a critical theoretical challenge. The barren plateau problem, well, it means that as you add more qubits to make your quantum circuit bigger, the gradients you need to train the network, they just tend to vanish exponentially.
And if the gradients vanish, what does that mean practically?
It means the network can't learn. The feedback the classical computer needs becomes flat.
You are listening to the AI World Podcast, your trusted source for the latest innovations, insights, and trends in artificial intelligence, blockchain, fintech, and decentralized technologies. Each episode features expert interviews, engaging discussions, and in-depth analysis of how AI transforms industries worldwide. Stay ahead of the curve with the latest articles and exclusive reports from the AI World Journal, covering everything from emerging technologies to industry breakthroughs. For more news, global events, and access to AI World Society circle gatherings, visit us at aiworld.tv. Don't forget to subscribe to stay informed, stay connected, and be part of the AI revolution with AI World Lounge. Thank you for listening.
Indistinguishable from noise. The network just hits a wall where no progress is possible. It's a huge problem.
And yet, research continues.
It does, because the potential is still there for certain types of problems. Yeah. We also have to remember, this synergy goes both ways. It's not just quantum helping AI.
Oh, right. AI is helping build better quantum computers.
That's a key operational point. These machines are so sensitive. Machine learning algorithms are constantly running in the background to optimize qubit calibration, automatically correcting for errors in real time. AI is even used to design more efficient quantum circuits. It's an acceleration loop.
Okay, so let's pivot to the industry dynamics. When we look at the landscape in 2026, 2 names really stand out, IBM and IonQ. They seem to have very different philosophies.
They do, and many experts see their strengths as complementary. The difference really comes down to their technology and their market approach.
Right.
IBM is, the established massive tech corporation.
Right.
Their technology relies on superconducting qubits, which are circuit-based and have to be kept incredibly cold.
And their vision isn't just about building one magic box, is it?
No, not at all. Their long-term vision is what they call quantum-centric supercomputing. They're focused on integrating quantum processing units, QPUs, directly alongside traditional CPUs and GPUs within their huge cloud and software stack. IBM brings the scale, the software, the integration.
So they're trying to make quantum acceleration a seamless part of the existing enterprise workflow.
Absolutely. Now contrast that with IonQ. IonQ is a pure-play quantum startup. almost entirely focused on hardware innovation. They use a completely different technology, trapped ion qubits.
Trapped ions, so their qubits are actual atoms held in place with lasers.
That's right, individual atoms suspended by magnetic fields. And the advantage there is that trapped ions generally offer higher fidelity and lower error rates. Because they're individual atoms, they're better isolated from external noise.
So less decoherence.
Much less.
Yeah.
So while IBM focuses on the scale and integration of many qubits, IonQ is obsessed with pushing the fundamental hardware performance, the quality and reliability of each individual qubit interaction.
So IBM provides the enterprise-scale infrastructure, while IonQ drives the raw hardware innovation. It's like a classic Goliath focused on scale versus a pure-play innovator obsessed with fidelity.
And that's exactly what the market needs. It needs both. You need the big integrated infrastructure for adoption, and you need that relentless hardware innovation to make the algorithms more and more powerful.
Okay, so while the promise is immense, we have to talk about the challenges that are still limiting full-scale deployment in 2026. What are the key technical hurdles?
Well, despite all the progress, hardware constraints are still stubborn. Qubit stability is better, sure, but the error rates still limit the depth of the algorithms we can run. How many steps you can take before errors just overwhelm the whole computation.
And the algorithms themselves, they still need to mature.
Precisely. Right now, QML algorithms often only show a real advantage on, on synthetic or small-scale data sets.
Yeah.
We haven't yet seen widespread, decisive proof on the massive, noisy, real-world data that enterprises deal with every day.
Then you have the economic side of it, the cost and the talent gap.
A huge issue. The cost of hardware and cloud services is still prohibitive for most, and globally we have a severe shortage of people who are fluent in both quantum computing and advanced AI. That talent gap might be the single biggest speed bump right now.
But if we had to pick one, the single biggest technical bottleneck slowing down QML progress, what is it?
I would say it's the data loading bottleneck. We still haven't efficiently solved the problem of how to load massive classical data sets onto quantum memory, or CARM.
Why is that so difficult? Why can't you just, drag and drop data into a quantum computer?
Because CARM is just fundamentally different. It requires the data to be meticulously encoded into quantum states. That process is extremely sensitive, it's slow, and it's resource intensive. If loading the data takes longer than the quantum calculation itself, which it often does, then your whole quantum speedup is gone.
So the advantage is nullified before you even start.
Exactly. Until we can load data quickly, the quantum advantage stays limited to problems of small inputs.
That makes perfect sense. Okay, let's transition to the highest stakes topic here. The ethical and societal implications. This kind of power, it just amplifies all the existing risks.
Absolutely. And the most immediate, most critical security concern is what's known as Q-Day.
Explain Q-Day for those who aren't familiar, and why isn't it just some far-off future threat?
Q-Day is the moment a sufficiently powerful, fault-tolerant quantum computer becomes operational. When that happens, using something called Shor's algorithm, it will be able to break our current public key encryption standards, RSA, ECC, the things that secure nearly all global communication.
So you're saying hackers or hostile nations could be capturing and storing encrypted data, financial records, military secrets today, just waiting for that Q-Day machine to crack it all open?
Precisely. That's why the transition to post-quantum cryptography, or PQC, is not just important. It is a critical and immediate security priority.
Right.
We're talking about protecting decades of archived data from an attack that is, for all intents and purposes, inevitable.
Wow. And beyond security, what happens when quantum speed meets biased training data?
You get bias amplification at a speed and scale we've never seen before. If these quantum-accelerated AI algorithms are trained on data sets that reflect our existing societal prejudices, they will amplify those discriminatory outcomes in things like hiring or loan approvals.
And because the system is so fast and the logic is so complex, that discrimination could become systemic before we even detect it.
It could. And then there's the opacity problem. The very nature of quantum computing makes transparency difficult.
The black box gets even blacker.
Exponentially so.
Hmm.
Quantum computation is fundamentally probabilistic. So explaining why a quantum AI system arrived at a decision becomes almost impossible. That lack of transparency really undermines accountability and public trust.
And finally, the digital divide. This technology is so expensive, the talent's so scarce. Where does all this power end up?
It inevitably concentrates in the hands of a few wealthy nations and large corporations. It risks widening the global economic disparity, creating a really significant geopolitical power imbalance.
So, to summarize our deep dive into 2026, we're entering this dynamic new era, driven by IBM bringing the enterprise scale, and IonQ driving the raw hardware innovation.
That's right. And this convergence is starting to show the potential to solve problems we once considered impossible, from real-time climate modeling to designing new medicines. The hybrid approach, especially with VQAs, is providing tangible benefits right now.
So what does this all mean for you? We've established that the inevitable Q-Day makes the transition to post-quantum cryptography a critical and immediate security priority.
And that raises a final provocative thought you should consider. If protecting decades of your organization's sensitive data from a future quantum attack is an immediate priority, how prepared is the world right now today to execute that massive global cryptographic transition necessary to avoid catastrophe? The theoretical future is demanding very tangible, very urgent current action.
The future of artificial intelligence is unfolding, and it's happening at AI World Week, the flagship global event for innovation, collaboration, and transformation. This flagship global AI event is designed to connect visionary leaders, trailblazing entrepreneurs, and influential thinkers to explore the endless possibilities of AI. Experience groundbreaking technology that redefines industries and inspires progress. Join thought-provoking discussions on ethical AI, digital equity, and the transformative role of technology in our world. Build meaningful connections that catalyze innovation and drive impact. AI World Week is powered by AI World Society, a global movement dedicated to advancing AI responsibly and ensuring it serves humanity. Together, we're shaping a smarter, more inclusive, and equitable future. Continue your journey beyond the event with the AI World Journal, offering expert insights, in-depth analysis, and the latest trends shaping the AI landscape. This is your opportunity to lead, to innovate, and to transform the world with AI. AI World Week. We invite you to join us and embrace the AI revolution.